As next speaker, we have William Lionheart and from University of Manchester, and he will tell us about computational challenges in rich tomography. Do you have William? Ah, perfect.
Can we find it? Oh, we love it. Right. Super. So you do it from the back, or? Yeah. Oh, we could use this control now. It's not on the screen yet, though. F5, okay. Function of 5. There's no action on the F5 here. Yeah. Brilliant. Thank you very much. Sorry for the delay. Okay, so following on from Laura's wonderful introduction, who's covered SIL and tomography in general, I'm going to talk about some kind of more future challenges and some things that we can do experimentally that haven't yet been integrated in SIL, but it shows that the scale of doing tomographic-like problems ranges across a very wide range of applications and different physical measurements as well. So rich tomography is a fairly new term. Tomography than poor tomography, right? It seems a very positive word. What I mean is, in scalar tomographic problems, typically we have a source and a detector. So we have lots of source positions and we have maybe a whole array of detectors, and we move these around. And we measure one scalar, how much of something gets through along that line. Right? So the idea of rich tomography is that we will measure a higher dimensional type of data for each line. So, for example, a polarization state, which would be a matrix, or a spectrum, or a diffraction pattern that's like a 2D spectrum, or a histogram or distribution of something. So there's a number of things that we can measure that are much richer than just a scalar per line, and that allows us to seek to recover something more complicated. So, for example, a function in reciprocal space of 3 variables in each voxel, or a vector such as a magnetic field or an orientation, a tensor such as a strain tensor, or, and Laura touched on this, the amount of each of a list of materials in each voxel. So these are a fairly wide range of things that we could measure and things that we might want, and that's what we mean by rich tomography. So some pictures here. I can, so first of all, this is called SAX, small angle X-ray scattering tomography, and the image is taken from Liebling, reference 4. So the point is synchrotron X-ray sources are setting themselves up to do this. They're investing hugely in this technology. What they do is they have a focused beam, which they raster scan, and then they rotate the object around 2 axes. And for each of those beams, they measure a whole diffraction pattern. Right? So that's a lot of data. And the idea is at each point in the voxel, you can imagine there's a function in reciprocal space, so in the Fourier transform variable, that gives the preferred orientations of the crystals, for example, in that structure. We can do these sort of things with electrons. We already do electron tomography in the SIL. Biological electron tomography happens mainly in the bright field of the electrons that are transmitted straight through. In material science, they generally look at the diffraction patterns already. And in this example, we're looking to measure the strain on a single crystal of silicon, because the strain determines the electron distribution and hence the properties of semiconductors. And the way we do this is thin electron beams that have a little diffraction spot, which is blurred by the fact it's gone through the strain. We do that from different angles, and then we try and reconstruct the strain in that sample. Polarimetric neutron tomography is kind of fun. I didn't know before I started on this that neutrons were anything more than like a little black billiard ball, but they have a spin polarization. And that spin polarization changes as you go through a magnetic field. And this allows you to measure the effect of a magnetic field. Sorry, to measure the magnetic field over the trajectory of the neutrons, right? So the spin state twists around as it goes through the magnetic field, but the neutrons go in lots of different directions. And so you can image a magnetic field. Synthetic aperture radar is also a kind of tomography. It's a rather strange one because it's electromagnetic waves at microwave frequencies. But that's also something that fits into the same framework. I'll say a little bit more about that later. I'll skip over neutrons because Laura's already mentioned them. Okay, so maybe the thing that I should say is that a pulse of neutrons come through and they cover a range of energies. It's rather easy to measure the spectrum of neutrons because the wavelength is related to the speed. They put these neutrons on a very long tube, and so the first ones to arrive are the fast ones that win the race, right? So all you need to do is time gate the neutrons to get spectral data, which is pretty neat. And the thing that we're usually interested here is the Bragg edge, which reflects the separation between the crystallographic planes. And when the sample's strained, this Bragg edge would move. But if it moves differently along the beam, because you have different strains, it actually blurs out this slope. And from that, we can recover the distribution of strain along that line. So a lot more than just the total strain along that line. So we can do that tomographically, and we have some results in preprint. So just an idea of the amount of data. The ISIS IMAP has a 512 by 512 pixels and up to 3,000 time of flight bins. So our data with the arrival times is quite big. In this case, we use 120 projections, but this takes hours of beam time. So acquisition is extremely slow, but also the data is quite large. Okay, I'll skip over. Okay, so those are material maps from time of flight neutron tomography. And this is recovery of the distribution of strain along one line. So it's quite noisy, but there is a signal in there. Oh yeah, okay, so this is fairly recent. We've managed to do strain tomography despite some difficulties, and there's a nice way to validate it. So in this column, we've got a ring and plug that's strained, and here there's an offset plug. So this has residual strain in it. This is a sort of sinogram data that you get from rotating it in one plane. And this is an independent method of measuring strain that's rather tedious because it looks at one voxel using a collimated beam. Very slow and tedious, but it agrees with this much faster tomographic method now. We've sorted out the theory. Okay, so soon to arrive in SIL, but we can do that experimentally, and we've done the theory. A little bit about electron diffraction tomography. This is just diagram I've said before. It's like using one beam, like in the SACS tomography, but we can use lots of beams at the same time as long as their diffraction patterns don't overlap. And in a way, you can see that because the diffraction spot is blurred by the strain in the direction perpendicular to the beam, we can back out from that a certain amount of summary information of the strain that it's gone through. Okay, so in this case, typical experiments on a modest scale might have tens of projections of thousands squared sensor positions. It's often reduced down. The diffraction problem is also nonlinear, and I suppose that's another computational problem, that a lot of tomographic problems, when you look at them carefully, are nonlinear, and some of them are just obviously nonlinear. So, of course, we don't just need iterative methods to solve large linear systems, but to solve nonlinear systems where the linear problems are a sub-problem of it. I would say a little bit about synthetic aperture radar, not that much. It's used for civilian purposes, for example, monitoring vegetation and crops and disaster scenes. And it's also used for military intelligence. We're thinking of volumetric SAR, which is a 3D imaging technique. It's multi-static, so we have transmitters and receivers in different places. Imagine we could fly them around on little aircraft or something like that. So lots of transmitter and receiver positions. As a tomographic problem, it's integrals over spheroids. I mean, ellipsoids, where the foci of the ellipse is at the transmitter and receiver. So imagine a rotated ellipse. And that's what we integrate over for one travel time. So instead of integrating along a line, we integrate over these surfaces. It's still a sparse matrix, but not as sparse as integrating along a line. And so that makes it computationally more challenging. The data and the image are both complex because we measure phase. You can also measure polarization of the microwaves. The scatterers might be anisotropic, and you do it over a range of frequencies. Typically, they use the equivalent of a filtered back projection, a Fourier method, but we're introducing the methods that we have in SIL that are iterative reconstruction methods. And just as a first taste of it, this was a simulation of some trees, buildings, and vehicles hiding in the trees. And so typically sort of 1,000 by 1,000 by 300 or something like that. So the height doesn't have to be as high as the ground resolution. Just to show that it works, that's one of the standard algorithms we use in SIL. Used on SAR data. I think it's time I stopped, isn't it? So tomography results, a huge potential increase in the scale of the reconstruction problems. And in many cases, people are investing huge amounts of money to achieve these rich tomography data, but without having really thought how they're going to do the reconstruction. I mean, I think the moral is partly you have to be cleverer, right? So we actually need to be clever from an algorithms and a software point of view, maybe measuring the right subset of data. But in particular, we're struggling with the Moore's law of computers against the Moore's law of sensors. So, you know, sensors are getting more high resolution, faster, more spectral channels, and we can't just wait for the computers to get bigger. Some of these problems have a natural kind of product structure, which suggests some parallelization, and systematic incorporation of prior information, stuff that you already know, is obviously a good idea. If you do it right, you can decrease the number of unknowns. I think I'll stop there about in time. Thank you very much.
That's great. Thank you so much for the great talk.